Good day, sir, and to everybody who's watching this video. So my problem for this day is about a hollow beam which is shown in this figure. So the problem will answer 5 questions that is related to our topics that you have discussed in our subject. So let's start. The problem is a hollow beam is shown in the figure. Assume F prime of C, which is that is a compressive force, 28 MPa or megapascal, and Fy is equal to 345 MPa. So the first problem or the first question is calculate the required tension steel area when Mu is equal to 800 kilonewton meters. Letter B, what is the balance moment capacity of the beam? Letter C, what is the maximum steel area under singly reinforced condition? Letter D, what is the maximum design moment strength under singly reinforced condition? And lastly, calculate the required tension steel area when Mu equals 1,200 kilonewton per meter. So this is the figure related to my problem. In this figure, we can see that the base of the beam, of the hollow beam, is 500 millimeters, and this is 125 millimeters. So as with this, and this is 250 millimeters. So the height or the effective depth of our beam is 800 millimeters divided by 150 for the bottom part, 150 for the upper part, and 500 for this section. So our first solution, so to check whether A does not exceed 150 millimeters, let us solve when A is equal to 150 millimeters. So our D is equal to 800 minus 75, which means the full length 800 minus the 75 here. So we will only solve for our beam from this area up. So D is equal to 800 minus 75, which is equal to 725 millimeters. So our Mn, or the phi symbol, times Mn is equal to phi times the compressive force due to concrete times D minus A over 2. So the extraction formula of this Cc is Cc is equal to 0.85 F prime of C times BA, which means the 0.85 coefficient here and our F prime of C, which is 28 MPa, times the base, which is 500, and A. So the value of A is 150 millimeters. So substituting the values, 0.90, which is the value of our phi, that is a standard for the steel beam. So 0.90 times 0.85 times our F prime of C, which is 28, times the A, which is 150, times 725 minus 150 over 2. So the answer for this equation is actually 2,088,450. So I will write it down. This number will be divided by 10 raised to the power of 6. So that we can attain the kilonewton meter unit. So 10 raised to the power of 6 is 2,088.45. We will divide it by 2 since there are 2 sections here. So the answer is 1,044.225 kilonewton meters. As you can see that the solution we have done earlier won't do something with the solution proper about our problem. So for this moment, let's start solving the question for letter A, which is calculate the required tension steel area when our moment capacity Mu is equal to 800 kilonewton per meters. So from our solution earlier, we can see that the Mu, or the required Mu, which is 800 kilonewton meters, is less than 1,044.225 kilonewton meters, based on our F prime of C, which is 28 times 10 raised to the power of 6 times this one that we have solved earlier. So that is when A is less than 150 millimeters. So in this problem, we have to assume that the tension still yields. So we will use the formula mu is equal to phi mn. So we will extract another formula for this problem so that we can easily solve and we can easily substitute the numbers. So we have mu is equal to phi times cc times d minus a over 2. So we will extract the formula again. So that will be mu is equal to phi times 0.85 times f prime of c a b times d, or the quantity d minus a over 2. So we will substitute all the values. That is our 800 kilonewton meters. We will convert this one into millimeters. So into Newton millimeters. So we will put it as 800 times 10 raised to 6. So that it will be equal with these numbers, which is in terms of millimeters. So the value of our phi, which is 0.90 times 0.85, then the value of our f prime of c, that is 28 MPa, times our unknown here is the letter A. We will solve first for A so that we can solve so that we can check if the still yields. So A times 500 times the quantity is 725 minus, so you know, 1/2, we can still write it as 0.5 times A. So through calculations, the value of A is 101.6 millimeters, and that is less than 150 millimeters, which is our first assumed value of A. So let us check if our steel yields. So we will use the formula Fs is equal to 600 times D minus C over C. So based on our figure earlier, this D has the value of 725. As I have explained, that is 800 minus 75. So that is 725. And our C, we can see here that C is equal to A over B sub 1. And the value of A that we will use for this solution is the 111.6 millimeters. So we will substitute for A, 111.6 millimeters. And the constant value of our B sub 1 for steel, that is 0.85, since our F prime of C. So as you can see, this B1 has the value of 0.85 when our F prime of C is less than 30 MPa. So the answer, 101.6 over 0.85 is 131.3 millimeters. So moving on, let us substitute all the values for D and C in our formula. Fs is equal to 600 times the quantity. So we can still write this formula into this form. So for D, we have 725. Our D is the effective depth of our beam. So it has the value of 725, as I've explained to you from this one. So D is 725 minus 131.3, the result of our C, over C again, 131.3. So through calculations, we arrived the answer 2,713 MPa. That is greater than the Fy. So therefore, our steel yields. So when our force of tension is equal to our force of compression, that is T equals C, so we can now solve for our required, which is the tension steel area AS. So AS, we will use the formula AS Fy is equal to 0.85 F prime of C times AB. So that is, since we already have the value of Fy here from our problem earlier, that is 345 MPa. So since our value for Fy is 345 MPa, we will substitute it here. AS times 345 equals 0.85 times the value of F prime of C, or that is the compressive force, 28 MPa, times the value of our A, which is 111.6, substitute, times our B, the base of our beam, that is 500 millimeters. So through our calculations using our calculator, we arrive at the answer 3,850 millimeters squared. Our unit here is millimeters squared since it is the area of the steel in tension. So let us proceed with answering the question for letter B. That is, what is the balance moment capacity of the beam? So balance moment capacity, we will refer this problem to our figure number 2. So we will refer this problem to our figure number 2, which is this figure. So I'm sorry for any inconvenience in this report because the space that our visual aid will be placed is not so wide. So as you can see that we have determined the neutral axis of our beam, and that is lying right here. So there are unknowns, which is Z, A, and you can see the value of the C1, C2, and T as we go along with this problem's solutions. So let's proceed to solving the letter B. So first, we are going to solve for C, B, that is the balance for compression, that is 600 times D over 600 plus Fy. So since we already know that the value of Fy is 345, so we will directly substitute the values here. So that is 600 times our D, 725, as you can see. So I'm sorry that this figure is faulty. 725 starts here. So that is 725 over 600 plus 345, which is our Fy. So through calculations, we arrived at 460.32 millimeters. So next, we will solve for our A. That is, we have the formula A equals B1 times CB. So we will substitute the value of B1, that is constant 0.85, times CB, which is 460.32 millimeters. So we will substitute it here. And the answer is A equals 391.3 millimeters. After that, we will solve for our Z, which is equal to A minus 150. So you may question that where did I get my formula for this problem? So it's all written in our module. So Z is equal to the value of A, which is 391.3 minus 150. That is 241.27 millimeters. Solving for our area 1, let us then solve for our Y1. As you can see, the Y1 here starts from this part of the beam up to this part. And correction, that is through the center of this area 1. So we have to solve, and by the way, I'm sorry if you can see some solutions here for letter C. So we will explain more about this later. So let's focus on this part. So we have our Y1 is equal to 725, this full length of our beam, or here, 725 minus the 1/2 of 150. That means 725 from here minus the 1/2 of 150, this one, because our length for Y1 that is being solved is from here up to the center. So that is 1/2, 725 minus 1/2 of 150. And that is 650 millimeters. So after that, we will solve for area 2, this one, as I have explained to you earlier. Area 2 is equal to 125 times 241.27. Why? That is the length of our Z. Our 241.27 comes from the length of our Z. That refers to the length of our area 2. So since it has a base of 125, So that will be 125 times z, which is 241.27, and that is 30,159 millimeters squared. After that, we will solve for our y2. y2 is equal to 725, and this part, for our y2, the length, or we will solve it from here to the center of this area, or just simply look at this figure. So y2, that is 725 minus 150 minus 1/2 times z. 725 minus 150, since we will not include this length, minus 1/2 of z, because we will only solve for this part down. We will not include the upper part. So that is 1/2 of z. So 725 minus 150 minus 1/2 of 241.27, that is 454.37 millimeters. Sorry for this unit. So, we will now solve for our balance moment capacity, that is MBN. MBN is equal, through the formula, is equal to C1 times Y1 plus 2C2 times Y2, because our Y2 here has two parts in this beam. So we have balance moment capacity. We have extracted the formula to this form. 0.85 times F prime of C, that is for C, right? Times A1 Y1 plus 2 A2 Y2. So we will use this formula for the simplicity of our solution. So that is 0.85 times the value of our FC, that is 28 MPa. Let us not forget the value of our FC, F prime of C, times the quantity, the sum of the quantity A1 Y1 plus 2 A2 Y2. So since we all have the values for A1 Y1, A2 and Y2 here, let us already substitute everything. 0.85 times 28, 75,000 for A1, 650 for Y1, plus 2 times 30,159 for A2, times 454.37 for Y2. And the answer is 1,812.52 kilonewton meters. When you are going to calculate this equation, you can arrive to many numbers in the calculator. So the tip here, you will divide that number by 10 raised to the power of 6, so that you can arrive at this answer. So I'm sorry, this isn't the balance moment capacity yet, because our moment capacity is from this solution. So moment capacity is equal to 0.90 times the value of our moment, which is 1,812.52, and that is 1,631.3 kilonewton meters. And that is the answer for letter B. That is the balance moment capacity of the beam. I'm sorry that I have emphasized it here, but actually the balance moment capacity of the beam is found right here. That is 1,631.3 kilonewton meters. So, let's proceed to our problem for letter C. That is, what is the maximum steel area under singly reinforced condition? So, our singly reinforced condition, we have this T is equal to C1 plus C2. So, we will solve for maximum steel area, which is AS max. So, first step, we are going to solve for the ASB FY. This is the area of the steel times Fy. So the formula is 0.85 times F prime of C times A1 plus 2A2. As I have explained, there are two areas for A2. That's why that is 2A2. So we will substitute everything for this formula, Fy, F prime of C, A1, and A2. So that is A times 345 for Fy is equal to 0.85 times the F prime of C, that is 28, or that is the compressive force, times the quantity of 75,000 plus 2 times the area 2, which is 30,159, as you can see it here. So we will calculate and we will arrive at the answer. We have arrived the answer 9,335 millimeter squared. So that is not the answer yet. So for solving the maximum steel area, so we are going to use the formula AS max is equal to 0.75 times the previous answer ASB. So AS max is equal to 0.75 times. We will substitute the value of ASB. That is 9,335. And we have arrived at the answer 7,001 millimeter squared. And that is the maximum steel area of our beam under this singly reinforced condition T equals C1 plus C2. This moment, we will solve for the problem or the question for letter D. What is the maximum design moment strength under singly reinforced condition? So we will solve for the maximum design moment strength. That is Mn max. So our singly reinforced condition here is C1 plus C2 that is equal to T. So the same formula from letter C. So in this condition, we will solve first for our new area 2. We will substitute for the value for the formula of C, and that is, I will write it again. For C, we have 0.85 times F prime of C, then AB. So in this, we will not literally use AB because we will solve for our new area 2. So that is 0.85 times 28 for the compressive force times the quantity of 75,000 plus 2 area 2. So in this condition, we have made area 2 unknown. So that is 75,000. Area 1 or the value of area 1 stays as it is. So we have 2 area 2 and that is 2A2 equals 7,001 times 245. And the answer is area 2 is equal, the new area 2 is equal to 13,244 millimeter squared. So after solving for area 2, we will now solve for Z. Using the formula A2 is equal to 125 times Z, we will arrive, since we have arrived at a new value of area 2, we will also arrive to a new value of Z using the same figure but in different solution. So we have area 2 that is 13,244 millimeters squared equals 125 times Z. So using our calculator, we arrive at 105.95 millimeters, and that is the value of our Z. We will now solve for our Y2 because we have arrived at new value of area 2, new value of Z, and new value of Y2. And that will be 725, the same solution as what we have done earlier, minus 150 since this is not included in our length, minus 1/2 of the new value of Z, 105.95. So our new Y2 is 522.3 millimeters. We will solve now for our Mn max or the maximum design moment strength. So that we have the formula Mn max is equal to C1 plus Y1 plus 2C2Y2. So we will extract the formula or we will rearrange the formula using the value of C here. So we have Mn max is equal to 0.85 times F prime of C or the compressive force times area 1 Y1 plus 2 area 2 Y2. That is the simpler form of our formula. So we will substitute all the values here using the old value for A1 Y1 and the new values for our A2 Y2. So Mn max is equal to 0.85 times 28, the compressive force, times 75,000 times 650 A1 Y1 plus 2 times new A2, that is 13,244 times mu y2, that is 522.03. So our Mn max here is 1,489.34 kilonewton meters. Another mistake, this is not the answer yet. This is not the maximum moment strength, and I'm sorry that I have repeated my mistake. So the real maximum moment strength, that is, we will use this formula. Pmn max is equal to 0.90 times 1,489.34, just substituting Mn max. So our answer is 1,340.4 kilonewton meters. That is our maximum design moment strength, and that is the answer for the question of letter D. At this point, ladies and gentlemen, or shall I say gentlemen, so we will solve for the last question, that is letter E, tension steel area, when our moment capacity is 1,200 kilonewton meters. As we can see, the required moment capacity here is less than our previous answer, that is 1,340.4 kilonewton meters. So we will already apply the values that have been solved earlier for A1 and Y1. So we have here A1 remains 75,000 millimeters squared, Y1 650 millimeters. And as for our A2, another value for our A2, that is 125 times Z. So as you can see, the length here or the width here is 125 times new value for our Z. These problems is also referring, or this solution is referring to the same figure as what we have done for our previous solutions. So the formula mu is equal to Pmn max. We will substitute the values in that formula. So we have, since our Mn max is 0.90 times this extraction of the equation, so we will only substitute for our required mu, that is 1,200. And since it is in terms of kilonewton meters, we will multiply it by 10 raised to the power of 6 so that it is the same with the units from these numbers. So that is 1,200 times 10 raised to 6 equals 0.90 times 0.85, that is our B1, times f prime of C, A1 Y1 plus 2A2 Y2. So rewriting it again, 0.90 times 0.85 times 28 for our compressive force, A1 75,000, Y1 650 plus 2 area 2. That is 2 times 125Z, our new area 2, times 575 minus 0.5Z. So that is for our Y2. So using our calculator, we arrive for the value of Z, that is 53.04 millimeters. And that is very essential for our next solutions. So we will use the next formula, that is AC equals A1 plus A2 times 2. Since there are two areas. So we have AC is equal to, we will substitute A1, 75,000 plus 125 times 53.4. As you can see, this is 125 times 53.4. That refers to our A2, which is 125 times Z. And since we have solved the value of Z, so we will already write the number for Z here, times 2 because A2 has two areas. So AC is equal to 88,260 millimeter squared. So when force of tension is equal to force of compression, that is T equals C. So our AS Fy is equal to 0.85 force of compression times AC. This formula will be used in solving for our tension steel area. So that is AS times the value of Fy from the beginning, that is 345 MPa, equals 0.85 times our compressive force, that is 28 MPa from the beginning times the value of our AC, and that is 88,260. So using our calculator, we arrive at 6,088 millimeters squared. And that is the answer for our last problem or last question in this problem. So I hope that I have shared new learnings to you, and I hope I have met the requirements for this subject, and I appreciate all the efforts that were made through this video and the considerations that were being extended to everybody. So this is Rayalyn Amarelie. Thank you so much.